So, do y'all have any questions on what we went over so far? Anything we need to go back over? Stop for a switch. Now, we're going to have several circuits, but what we're playing around with now, we're playing around with a saturated switch. So, when we use a transistor as a switch, we're going to switch it between saturation, which means it acts like a closed switch, and cutoff, which means it acts like an open switch. So what we're doing is we're just trying to figure out what quantities of resistors or whatever we need. So let's say we're going to come up here and we wanted to turn on an LED. And having the forming sheet is good, but being able to logically figure it out and do it on your own is better, right? So what we say, let's say I want to turn on a transistor or turn on a light emitting diode. And I want to do something that provides very, very little current. So we do this a lot. So you have to understand that everything you see up here is being controlled by a transistor. So these things, I brought you up here and put my microscope up there and let you look and see all the little triads, right? All the little dots. Well, for every one of those, there's a transistor that turns it off or turns it on. And that's all it does. The more red's inside a pixel you turn it on, then the darker the red will be, right? And then we might do red and yellow and do different triads to come in and get different colors. So let's say we're going to do something similar to that. So let's say I'm going to bring in over here. I'm going to bring and what's nice about an LED is what you put on the collector and what you put on the base does not have to be the same the same power supply. They have to have the same common, but it does not have to be the same power supply. So let's say I come over here, and what I'm going to do is I'm going to come over here and I'm going to put plus 5 volts over it, which is standard in TTL. I mean, transistor logic, 5 volts equals 1, 0 volts equals 0. So now we can get into digital, right? And I'm going to bring this over here. And then we're going to come up here. And we're going to put a light emitting diode. And then we're going to come up here and we're going to connect this to plus 12 volts. So the voltage levels don't have to be the same. They just have to have the same common. So I look at my trainer over here. I got plus 5 volts. I got plus 5 volts, plus 12 volts, right? I got minus 12 volts. I have a clock generator and I have a sine wave generator, and we only have one common. So they're all common together, right? Does that make sense? So I know this guy right here is going to only drop approximately 2 volts, and we'll try to put close to 15 milliamps out of it. So what does that mean? This guy drops 2 volts. We're going to set this up to drop 0. What does that mean we got to have in the circuit? No, 12 volts is given. This would be like saying, okay, on my car, I got 12 volts, but I want 10 volts. Well, we could do it with a Zener diode, but this guy drops 12 volts. This guy's going to drop approximately 0 volts. This guy's going to drop 2 volts. I'm going to put 12 volts up there. What do I need? What do I need to add to the circuit? A resistor. Yeah, so we got to add a resistor to drop the difference between the applied voltage and the voltages in the circuit, right? So this is what we got to figure. We got to figure, okay, I want to choose a resistor that drops what? 10 volts at 15 milliamps. So according to Kirchhoff's law, if I have 12 volts there, I have 2 volts here. When we saturate this thing, it's going to be about 0 volts. Then I've got to come up with a resistor that's going to draw 10 volts. And what are we trying to get for our LED? We're trying to get 15 milliamps. So what size is that resistor? And we'll call this resistor RC, because it's in the collector. So let me erase some of this stuff so I can put my RC over here. Caught my slant. Oops. So we know RC's got to drop 10 volts at 15 milliamps. And we know this guy here, we'll call this LED. We'll call this D1. This guy here, we know that it's going to drop about 2 volts at 15 milliamps. Okay, so what size resistor would I use? R is equal to Ohm's law. R is equal to V over I, right? That's the kind of question, guys, in this trade, if it takes you 10 hours looking at Ohm's law and swapping those cards out, that should be, in electronics, that should be almost like me saying, what is your name? And you say, well, no, you shouldn't even have to use that. For Ohm's law, you've only got 3 equations that you have to learn. So you don't see me pulling out a formula wheel when I say, how do I solve for R, right? You understand? You say, well, you're teaching the class. But if you go in and you went into an interview and a guy says, okay, you know, how do I solve for voltage if I know current? And you have to take out a color wheel and move it around and stuff like that. I think I told you about the guy. We used to have a competition here. It was for trade schools. It was called RETS. And they were up off the interstate in Inslee right there. And they didn't teach the resistor color code. They told them to go to Radio Shack and buy one of these little color wheels. I wish I still had one. And it had three little spots on there, and you would turn it until the color popped up, and then you would read the resistance value. So we have an employer, this is a true story, had an employer call them, and he said, don't send somebody that's got to use what? A little color wheel to know how to give me the resistance value. So knowing Ohm's law and knowing Watt's law, that should be Ohm's law especially, because Ohm's law tells us, even though I don't write it down, it gives us an indication of how does voltage affect the circuit, how does current affect the circuit. So if you understand that, then you don't even have to solve it now. You know if voltage goes up, what? Current's got to go up, the resistance goes up. So what did we count? So we know that R is equal to V over I. So that's why on your formula sheet I don't give you R, I don't give you R. I don't give you Ohm's law. I don't give you Watt's law. So what size resistor did we come up with? 667 ohms. Odds are there's no such thing as a 667 ohm. So what we've got, guys, I could come up here and I could set exactly 667 ohms with a rheostat. A rheostat would probably cost me $5. A standard 5-watt resistor would probably cost me a nickel. We buy them in groups of 100. And we'll look at the price. So, am I going to pay $5 or am I going to use a standard resistor? Huh? I use a standard resistor, right? You understand? Because here's my competition. They're using standard resistors. Here I'm over here putting a $5 pot on there. I'm selling mine for $15. My competition is selling theirs for $3, and they do exactly the same thing. What you gonna buy? So these engineers, they're going to use standard parts, and they understand that's going to. So our math is going to be perfect, right? You understand? But our components are what? Are not. So we understand, okay, it's not going to be exactly what I designed. So we'd look at our LED and say, okay, what would the LED handle? Well, it could probably go up to 20 milliamps, and it could probably go down to 10, and it would still light up. So here, all we're going to do on the LED is we're just going to round that thing to the closest standard value. Sometimes we might round up, sometimes we might round down. This R right here, we're going to get us one, and we'll solve for one, and then we'll choose a standard value. Here, we're probably going to do what? Here, we're probably going to round down, because we want this thing to assure saturation. Okay, so what size resistor? 660? What's the closest thing we can get to that? So 680. Because we're just rounded, right? You understand? So what does that mean? 680, it means it's going to be a little less than 15 milliamps. Okay, so now I got the size. What else do I need to know about that resistance? Tolerance we're not going to worry about. It's a 5%. We know it's not going to burn up the LED if it's 5% high or 5% low. In fact, you wouldn't even be able to tell the brightness. What else do I need to know? Make sure I get the right watt. What's the three things resistors are rated in? Tolerance, watts, and ohm. So we're not concerned with the tolerance here, right? You understand that? We're definitely we're definitely concerned about the R value, so we better calculate the wattage rating of that thing. So 680 is a little high, but 667, but 15 milliamps, even though it's not going to be 50 milliamps. I square R, you can come up and see what the wattage rating on that should be. So what should the wattage rating be? The minimum. It doesn't mean you can't go up, it just means you shouldn't go what? Down. Because we have standard wattage rating. We have an eighth of a watt, we have a quarter watt, we have a half watt, we have a 1 watt. I should have brought, when they get on up there, they start looking different. So what would be the wattage rating for this? What's the calculated wattage rating? It can be 150 watts. We only got 15 milliamps. Could be milliwatts, yeah. 150 milliwatts. So we use quarter watt. So we use quarter watt here. Yeah. Usually when you deal with milliamps, most of the time you're going to end up with milliwatts. So I'm not saying you always will. You know, if that was a 50,000 ohm resistor. Okay. So 680 ohms, quarter watt, we're okay. Okay, so now what we need to know is we're going to get about 15 milliamps over here. It's going to be 15 milliamps is okay. We know we're going to use, now we got to figure out what transistor it is. So what ratings of the transistor are we looking at? So transistors have all types of ratings. But there's only really, on a saturated switch, there's only a few of them that we're concerned with. First of all, what type of transistor is this? An NTN or PNP? Is the arrow pointing in or not pointing in? Well, we don't say pointing out. We either use pointing in or not pointing in. Okay, so this is an NTN. Yeah. Yeah, so if the arrow points in, we say it's not, right? You understand? It's either pointing in or not pointing in. So this one is not pointing in, so we know it's an NPN. We could do this with a PNP, but instead of being 12 volts, that would be minus 12, and the diode would be flipped around, but the calculations would be exactly the same. Okay, so we're going to use, since this is only 15 milliamps, we're going to use a 2N3904. So we've chosen a transistor. We chose these, of course. We have tons of those. So you can see why I chose a 2N3904. We got plenty of them, right? That's the 3906. This is 39. So we got plenty of them. I know, so I'd look at the data sheets, and I'd make sure the collector current can handle it when it's saturated. I think this thing is rated at like 600 milliamps, so we're well within the limit. And we're going to be interested in the beta. The beta is, we're going to look for saturated switch, we're going to look at the minimum beta. And the minimum beta for this guy is 30. Is that 30 amps, 30 volts? That, it's a multiplier. It's either a multiplier or divider. It has no unit. So gains doesn't have a unit. Now we do have something we'll learn later on. It's called dB. Have you ever heard of dB? Decibels. You ever heard of dB? If you've been in audio equipment, yeah. If you're in audio equipment or anything like that, you've heard of dB. Well, dB is a form of engineering. It's another way that we can represent very large gains without using a lot of digits. So it's a lot like engineering or scientific notation. So it'll look like it has a unit, but it don't, right? So it'd be like us using milli or micro. That's not a unit. That's just a size, right? You understand that? So y'all learn about dB in this class, because when we start talking about amplifiers, we're going to have to know about dB. So now we got everything we need. So I know this guy over here. We know, according to Kirchhoff's law, this is 0.7. We're putting plus 5 over here to saturate it. So how much is that resistor right there going to have to drop? 4.3. Good, yeah. And we'll call this RB. So VRB is going to be equal to approximately 4.3 volts. At what current? So to calculate the size of the resistors, according to this, R is equal to V over I. Well, I know the V, so now I got to do is figure out the I. So what would the I be? I, okay. So we know that this thing called beta, this is the current gain of the transistor. We know it's equal to what? IB or IC divided by IB. So we know the beta, we know IC. So now I need to rearrange this equation and solve for IB. So this is a new equation. So everything we've done so far is what? Kirchhoff's law, Ohm's law, Watt's law, and you should have learned all those things back in DC. I didn't say you did, I said you what? Should have. Okay, so we got 3 currents in, so we call this guy right here. This lead right here, what's the name of this lead right here? So these leads have names. They don't have numbers, they got names.
No. Yeah, collector.
Yeah, it's the collector. This guy right here is what? Emitter, good. And then this guy right here is the what? So base is controlling the valve. Takes a bit, but we have a big gain over the base current over the collector. So when I'm talking about the emitter current, I'll call that IE. This is the emitter current. IC would be the what? Collector, good. And then IB would be the base. So I see. So this will be the collector current. So what we just did is we set the collector current at somewhere around 15 milliamps. So the 15 milliamps was part of my design, right? You understand that? So that's IC. Which is the largest current in the transistor? So we use the same common. So we have two. You notice these two power supplies. So if I was to draw the entire circuit, this is what I would come up with. Except this right here would be 5 volts. This right here would be 12 volts. So this is the circuit that we have wired up, and of course, we got the LED right in here. And currently, we don't know this one, and currently we calculated this to be 660 ohms. Okay, so this is the circuit I got right here. So I got two power sources here. I've got a plus 5 volt power source, and I got a 5 volt power source. So if we follow electron flow, it comes out of this guy right here. It's looking for the positive. It flows up through the emitter, and it goes this way. So there's IB. If I follow the collector current flow, I'm going to come out the 9, go up through the same common. So that means this is IB, this is IC, and then we come up and go through right there. Well, this is IC, this is IB, so what's the emitter current? Emitter current is equal to IB plus IC, according to Kirchhoff's current law. So these currents add up. So I see that plus sign. So IE is equal to IB plus IC. That's a C, guys. So it's got to be the largest one, right? You understand? If I transpose this, then IC is going to be equal to IE minus IB. So there ain't nowhere in the world IC is going to be greater than IB, right? And if we transpose the other one, then IB would be equal to IE minus IC. So the emitter current is the largest current in the transistor circuit, always. Because it's the combination of base current and collector current. That will be on the test, guaranteed. Everybody okay? And that should be on your formula sheet, where it says IC, IE, so that should be on your formula sheet. But seeing on the formula sheet's okay, but understanding the operation, then the formulas make sense, right? Okay. So what we're saying right here is that this is a new formula. It's the gain. Gain is always out over in. It's always out over in. So in, we're putting IB, that's our input current. IC is where our load's connected. So this is beta. And what we're going to assume, guys, so over here, I think we looked at the circuit over here. I had like 100 microamps. And over here, I think when we had our circuit up here, I had like 10 milliamps. Right? I'm sorry, we had 10 milliamps right here. Over here, we might have had 10, right? Point, what? 10.1 milliamps. So for all practical purposes, 10.1 milliamps on the emitter, 10 milliamps on the collector. So what we do in formulas is we just assume they're the same. Because there's not going to be enough difference to affect our math, right? You understand why? Yes or no? So beta, is beta a fixed unit? No, beta's all over the place. Is my resistor, is that going to be a 1K resistor? No, that's not going to be a 10K resistor. Is that going to be a 1K? Is that going to be a 10K resistor? No, it's not going to be a 10K. So what we're saying is that all we do this whole time, every device that we deal with has a tolerance. So for math formulas, when we need to, we're going to say, IE equals to approximately IC. They're not equal, but they're so dang close that we can usually ignore it in that form. So if you see a question that says IE equals IC, you better answer false. If you see a test question that says IE equals to approximately IC, then that's going to be true. They are not equal. But they're so close that they are approximately equal, right? You understand? It's like saying $10 and a dime is approximately equal to $10. So I know IC, I know beta. We didn't look it up. But since we used that on Tuesday, we went ahead. We're going to use minimum beta here for the 3904. And then we're going to transpose this thing to solve for IB. So IB is going to be equal to IC divided by beta. Beta is going to be, IB is smallest. So this equation right here makes sense because beta is going to be big, right? You understand? IC is going to be small. And I know base current's got to be smaller, a lot smaller than collector.
And what is the
Huh?
So how do I find the factor?
Okay, let's.
It's in there already.
No, it's not in there. That's a rating, right? You understand? So how do you find the tire pressures on your car, on your tires?
Push it down on the first
What's that?
tool, the first down on it.
Well, that don't tell you what it's supposed to be. That's what it measures, right? How do you know what it's supposed to measure? I should have said that. It's in the loop, right? It's around the outside of the tread. So we look it up. So we know we got all these data sheets out here. So what we would do is we would go out here and we would look at the data sheet. And y'all got them on Blackboard. You've also got it in this data book over here too. If you'd rather use that than look it up on Blackboard, right? So data sheets 2 and 3904, and that's, so I took for granted y'all remembered this from last class, but I'll just, assume, you know what they say when you assume, right? So 3904, we're using the TO92 case, and I'll give you all these different cases. TO stands for transistor outline, and these are JEDEC registered cases. So JEDEC is the Joint Engineering Device Council. So what you can do is you can register your package up on JEDEC, and once it's registered, it's open technology. So that means if I had a 3-lead device, like a voltage regulator, a triac, a DIAC or something, instead of me designing my own transistor case, I could use this. And the molds and everything are already out there. So we got all these standard cases. Now what's nice about a standard case is now I can design a printed circuit board, right? So I can use an application that would design a printed circuit board for me and do all the spacing and everything for the holes for me. So those are out there. But that's only if I use what? Standard cases. So we need to check to see the breakover voltage. So this guy here's got a breakover voltage of 40 volts, always safe. So what's our collector voltage? When we turn this thing off, so the breakover voltage is when you turn the transistor off. So this guy right here can drop, when we turn this thing off, it's guaranteed that it can block 40 volts. How many volts do we have? We got 12 volts. So 3904 is great. So that's one measurement that we're very concerned with, right? Is the breakover voltage. How much this sucker can block, especially with a saturated switch, how much can it block when you turn the thing off? Okay. We need to have one that's got a beta of at least 30. So we're looking at minimum beta. So for saturated switches, so there's one thing we're going to measure. We're going to make sure. Also, the breakover voltage emitter to base. So if you ever reverse bias the base, this guy is very, very low. This guy, if we put more than negative 6 volts on a 3904, it could break over. We're looking for the maximum current. So this guy here can handle, I said 600 milliamps. 200 milliamps. We're okay there. We only need what? 15. So we're okay. So that's, right. And then we're looking at the beta. So they call it HFE, which is the hyper thread multi, but it's just beta. So the problem is you got to figure out. So HFE, most books call it beta, but just about all data sheets call it HFE. So that's something you need to know. HFE. So it's the, what is it? I can't remember that. Forward transfer ratio with the emitter common. That's what they say. So we're going to use minimum beta because we want to guarantee saturation. So on saturated switches, we're going to use minimum beta. Minimum beta is guaranteed. These other betas are not. So notice these are minimum, and these over here are maximum. They don't give us a tip. Are we okay?
Minimum
30. Right. That's what we're going to use for a saturated switch. So a saturated switch gives us the current gain between the base current and the collector current. So let's say I use a beta of 100. So that means sometimes this thing would saturate and sometimes it won't. So what we're trying to make sure that this thing saturates, whether it's wintertime, summertime, anytime like that. So saturated switch is, so if I get a beta of 100, I designed a beta of 30, so we're fine, right? You understand? So this is like we talked about in class. This is like minimum wage. So if I go to work, I expect minimum wage, right? I'm guaranteed minimum wage. It don't mean they can't pay me more. It's just that I'm guaranteed what? Minimum. So we'll go back and so like I said, so we know we're okay. We know we can block 12 volts because the thing can block up to 40 when we turn it off. And we're going to turn this off. It's a switch, right? You understand? Well, we know that it can handle 15 milliamps because it's rated at 200 milliamps. So you always, on that one, you always want to get a transistor that's rated higher than what you're doing, right? You're designing right. And we know that the beta is 40. I'm sorry, 30. So IB, what we're going to do for IB is we're going to take our collector current. So IB is going to be equal to approximately 15 milliamps divided by 30. So what we're going to come up with IB? 500 microns. Okay, so RB, I want it to drop 4.3 volts at 500 microns. So what we got? Four point three. Yeah. Because this guy here, we have 7/10 right here, right? I think this guy's got to drop 4.3. 8.6K. So what size are we going to use? Is 8.6K, is that a standard resistor? .2. We'll see what we got. I'll hook this circuit up when we go to lab. Wattage rating, we'll use a quarter watt there. It's probably gonna calculate to be an eighth of a watt, but we don't have any eighth of a watt. So we're ready to roll with this circuit. So what should we expect to happen? So that's all our math. We've calculated the circuit. So RB up here, we're going to use we're going to look for an 8.2K. I might have one of those and not. If I don't, but what happens is we're dealing with Kirchhoff's law. So what happens, I know there's a p-n junction right here. So right here, if you can look at this, there's a p-n junction right there. And this is a silicon, for silicon, right? Now they do have germanium transistors, by the way. If it's germanium, we use 0.3, but the 2N3904 it uses silicon. Silicon is by far the most widely used now because it's a lot more stable over temperature. So we use Kirchhoff's law. If this guy here, if you apply 5 volts right here, this drive drops around 17, it's 5 volts right there, then that means that guy goes up to 4.3. Okay, any questions? Pretty straightforward. Well, something new, but basically, and this is what's so neat, is we teach you all these formulas back in DC, right? And those are just, what does resistors do in a DC circuit? They do, what type of work does a resistor do? Huh? Work. Well, when we talk about work, we're talking about work. I know work is a rate, right? So what type of electrical work does a resistor do? Creates heat. That's all it does. Resistors create heat. That's the work they do. Now they have a function, which is what Janet says. We have a function, a limited circuit, but the work they do is create heat. These guys right here use that same feature that you learned in DC, but now we're controlling things with them. So we got this bipolar transistor. We can use resistors to bias it and make it work the way we want. So a bias does not mean you're biased towards something, but in electronics, bias means it's a DC voltage that you apply to a solid state device to control how it operates. It's its operation parameter. So now these things have a function besides just generating heat. They have a function in life, right? Of course, generating heat is good. So if you got an electric heater, that's all it is, just nothing but a resistor. It's just made out of something that's got a pretty good deal of resistance, and it don't melt like copper does. It's usually made out of like tungsten or something like that. So like I said, we got all these parameters, so I'll write them down, and then I'll go and see what we got, and then I'll look it up. So first of all, what should happen if we come over here? So 5 volts turns it on, 0 volts turns it off. So what should happen when we turn it off? Well, when we turn it off, then how much collector current, how much base current would I have if I put 0 right there? This would be something y'all need to be just like Zero. IB would be equal to zero. My collector and my base and my emitter are at the same polarity. So they're not first. How much collector current would I have? Zero. Yeah, so if zero, right? What would the LED do? Turn off. It's going to do something. It's going to turn off, right? Okay. What would be the voltage drop across the diode? C zero, right? What would be the voltage drop across RC? V is equal to I times R. We have no IC. We have an R, but we have no IC. So what would the voltage drop be across RC? Zero. What would the voltage drop be across transistor? It's the open element in a series circuit. So if this guy's dropping 0 volts, here's 12 volts. If this guy's dropping 0 volts, this guy's dropping 0 volts, then what that means is, that's going to put plus 12 volts right there. So that's why the total voltage is dropped across an open element in a series circuit. It's not because current flows through it, right? You understand? It's just that nothing in the circuit is dropping any voltage. So I mean, if I go over here to this light switch over there and I open it up, I'm going to measure 120 volts across the switch because these guys up here are not dropping any watt, not dropping any voltage. So that's why you measure the total voltage across an element, an open element in a series circuit. Helps us find opens, really. Resistors burn open, helps us find. Helps us find wrong fuses, really. We had a fuse when I worked in I worked in an electronic shop out of U.S. Steel. We had a transmitter. They had radio control cranes. I might have told y'all this before. That sucker had a fuse in it that was the current rating was so small that if you checked it with an ohm meter, it would blow. So how did we tell it was blown? Well, we measured the voltage drop across it. If it was dropping whatever the batteries was, we knew it was blown, right? If it was dropping close to 0, we knew it was what? We knew it was good. So we checked it with power. You can do this in your car. So instead of pulling those fuses out, and, even your little tab fuses that we use now, you notice there are 2 little tips up there that you can get to with a meter, right? You understand? So you can just go through there and do what? Just measure with your meter. If it's dropping 12 volts, it means just what? If a fuse drops 12 volts, it means just what? It's blown or open, yeah. So I've seen people pull that out and try to look at the element to see if it's blown, right? You switch it to what? We're measuring volts. Well, the AC voltage, you just flip it to AC, right? So whatever unit you're measuring, that's a good question, Carl. Yeah, whatever you're measuring. So if you're looking to see, if a circuit breaker's bad, I've had circuit breakers go bad, and it sets on, but when you measure across it, it's dropping 120 volts.
So it's like something that might have like 10 milliamps off. So you turn your unit to a foot.
No, we're not even using amps. What I'm saying is an open element in a series circuit drops the entire voltage. So a fuse could be rated at 1,000 amps. But I can check to see if it's blown by just putting my meter across it. So if it's 240 volts at 1,000 amps and I measure across it and it's 240 volts, it's what? It's open, yeah, or blown, yeah. If it measures 0, it either means power's not on or the fuse is good or the circuit breaker's good. So I've had several circuit breakers that gone bad. And they're set, right? You say, well, the circuit breaker's not blown. Well, if you measure across it, it should measure what? It should measure close to 0. Now, fuses won't measure 0 because fuses deal on I square R. This is what melts the fuse. So it's got to have an R component. So fuses will drop a voltage, but it's going to be very little. The lower the current rating, the more they'll drop. So you got a 10 milliamp fuse, it might be 10 ohms. But 10 milliamps times 10 ohms is still no volts, right? You understand that? So the lower the rating of the fuse, the more resistance it's going to have. The higher rating of the fuse, the less resistance. don't have. So these big old fuses, they'll measure 0 on our meter. So this guy's turned off. It's blocking the voltage. 12 volts across the transistor. It's okay because it's rated at 40, so everything's hunky-dory. Very simple circuit. You see different arrangements. So this could be being run by a digital circuit, that can only give out. So most digital circuits are rated like their output, a maximum output is usually around 10 milliamps. Nope, sorry. I need to go back and look at that. Oh, for a high, it's like 400 microamps. So for a low, it's like 10 milliamps. But for a high, for a digital circuit, these are nice big digital circuits too. These are, I don't have any out here. I don't think. So when or if you take digital electronics, you'll learn about the specifications on the integrated circuit. So 400 microamps, we couldn't do much with a 400 microamps, but we could run it through a transistor, saturated switch, and now we can do a lot, right? You understand? So I could get up to 200 milliamps out of this thing. Are we okay? This could be a switch. It could be used. It wouldn't make much sense to use a transistor to turn on something that a switch would do. But a switch takes somebody for you to turn off and on, right? This guy right here, we're turning this thing off and on electrically. So where does the 5 and the 0 volts come from? It could come from a sensor. It could come from a photovoltaic cell, even though we don't have one that put out 5 volts. Could be coming from a thermistor. And then now we're electronically controlling it. So any questions on this, guys? Well, think about this. Think about how many transistors are in this thing right here. They're usually not bipolar transistors, but they're transistors. So when you say you got 8 gigabytes of memory, that's one transistor per storage cell. That's either what? Off or on. PLCs, you're driving a bunch of stuff with what? With digital, with this stuff right here, this 400 microamps. So what's on the output? We're going to have these nice bipolar transistors either syncing or sourcing, right? You understand? So by far, the most used, since digital has came along, the most widely used thing is using it as a switch. So that's all digital is. But now, instead of me flipping the switches, it's what? It's electronically controlled. So that PLC, you don't see the transistor. All you know is either the output is what? Off or on. So that's a really good question. But you get into analog devices like stereos and stuff like that, those are analog. Even though the insides of them might be digital, by the time they hit those speakers, guys, that's analog. That cannot be digital going to those speakers. Those speakers respond to that. So in audio, probably this is where you're going to run into the most, probably bipolar transistors by far. We do have FETs we'll talk about. The FETs have a real high input opposition, so we'll talk about the advantages and disadvantages of FETs. So as far as computer memory goes, it's predominantly field effect transistors. If I need to drive a lot of current and handle a lot of power, then it's probably going to be bipolar transistors. So that's still the big advantage of bipolar transistors. The problem we have is when we saturate a transistor, so normally what we're supposed to do is we're supposed to keep this guy here reverse biased. When we saturate the transistor, then this guy here is going to drop a little less than 1 volt. So I might have 0.1 volt right here, or 100 millivolts right there. And then I've got 0.7 of a volt right there. So what actually happens when you saturate a transistor, it actually forward biases or tries to forward bias, it'll never get 7/10. They'll try to forward bias the collector's base junction. So it stores the charge there. It gets a lot of majority carriers there. So when we turn this thing off, it don't turn off instantly. It's got to discharge that collector charge. So these guys right here, once you saturate them, it takes a minute time to unsaturate them. So you can't switch them on and off. You can switch them off and on. Really, what to us seems like real fast, but inside computers, we're in a nanosecond world inside those computers. Reminds me of one of the Star Trek movies where Data was saying, and he says, I don't know if y'all, they thought they converted him over to a Borg, but he said, how long did you consider that? He said about 100 milliseconds, and he said that's no time at all. He says in the world of an android, that's a lifetime. So we can't already visualize how fast these machines are running now. So guys, questions? Yes, no? Oh, saturated switches. These are probably, like I said, in audio, it's predominantly these transistor circuits that we'll look at. In digital, these are the guys that use. So I think I'll show. These are the actual. Yeah, so this is the actual output of a DC module for PLC. And we talked a little about that. So this is plus, pointing in, right? Pointing in, P and T. So that means I can turn this sucker on just by putting, this right here is, so this has got to be negative in respect to this. So that means if this guy right here is setting it, plus 24 volts, then I can put anything below plus 24 volts to turn it on. And of course, what happens here is that, so we call this guy forcing, right? And then this guy right here, we turn this on, we have to turn this on with a positive voltage. And then this guy right here is syncing. So when you buy PLCs, that's one thing you specify, whether you want your input synced or sourcing or are they configured. And then when you buy the sensors, the solid state sensors, you specify either NPN or PNP, and you have to know the difference. So we have some PLCs where this is configurable, then we have other PLCs where it's fixed, where you don't control it. So this is something you need to understand when you buy the PLC too. So they'll have the same model as either syncing or sourcing. Okay guys, I'll take a 2-minute break, and we got just one more thing to look at, saturated switches, and then we'll go to lab. Got to show y'all how to check these things with, what we can do is we can take, and we'll use NPNs. This circuit is used so often that you can buy this in one device. And what they'll do is they'll take the emitter of this guy and they'll feed it directly into the base of another. And then they do different things up here. A lot of times what they do is just connect the collectors together. Sometimes they'll put a resistor up there. No, not the collector, I'm sorry. Because the collector is where we're going to put the load. So what would be the advantage of this? This is called a Darlington pair, by the way. So Darlington transistor. So if you buy a Darlington transistor, that means it's either going to be 2 NPNs or 2 PNPs. So what would be the advantage of this guy? Well, you don't ever see this emitter right here. This emitter right here will be, well, if you wire it, you'll see it. If you buy the transistor, guys, this guy's going to come in, and it's going to be 3 leads. Now, what's important about this is you can't check this guy with an ohm meter, because you're breaking down 2 junction. We had a printer that used the Darlington pair to fire the hammer, and it was drawn as a regular transistor. So I pulled it out and I checked it with my ohm meter, and it checked bad. I put another one in there, it did the same thing, because the transistor was a Darlington transistor. So then I looked the part up and said, well, that's Darlington, so that's why I can check it. But what we get out of this one is, let's say we come over and put it right here. And this would be my load. Let's say this transistor right here has a beta of 30. This transistor has a beta of 30. What would the base over here say? So let's say I come over here. And I'm paying you $1 out. And I triple your salary. So I'm going to multiply it by 3. Right? So now you're making what? $3 an hour. Then I triple your salary again. Are you going to be making $6 an hour? So gains, when you go through multiple gains, they are multiplied, guys. So if I come up here and triple your salary again, you're making $9 an hour. So what we would do, the total beta of this circuit would be 30 times 30. So what the beta of this circuit be? It would be 900. So that means if I put 1 milliamp over here, I could get 900 milliamps over here. So this is a very widely used circuit, because what we can get is we can get extremely large gains out of these things. Extremely large. I've seen these suckers have gains of like 10,000. So that would be 100 times 100, right? You understand that? So 100 betas are pretty interesting. 10,000. And then it's got some other features too. So this is called a Darlington pair. And it'll come. I mean, we can look them up, but it'll look just like a transistor. Because all we need is these leads right here coming out, right? So this, I got this drawn wrong. Normally it's like this. Oops, sorry. It's closed. The 2 collectors won't be connected together. I was right. So all we would have, if I come over here and put, and this one comes out, all we still have is what? If this is done internally, then all I'd still have is these 3 leads. So Darlington pairs. These are called Darlington transistors. And then of course I showed you the constant current source, right? I'll wire this up. This is not a saturated switch. This is where we operate this in the active region. So this is the active region. So we got 3 regions we can operate the transistor. What's the 3 regions? That sounds like a good test question too, right? What's the 3 regions? Huh? The 3 regions we can operate the transistor in. No, that's the 3 arrangements. Yeah. That's saturation. Cut off. And active. So cut off, it acts like one of these guys. Saturation, it acts like one of these guys. Cut off, it acts like one of these guys. saturation, active, it acts like one of these guys. So switches, we switch them between saturation and cutoff. That's what we do for a switch. This is analog, guys. When we run it as a rheostat. So this, we assume if it's less than 1 volt, it's saturated. This, if it's equal to the power supply. So if this is equal to approximately VCC, we call this cutoff. And this is going to be between 1 and VCC. VCC is the collector voltage. VDD would be a base voltage. And VDE would be an emitter voltage if we had one. Yeah. So when we identify voltages, then we go over this. In other words, so VC, when we duplicate this number right here, this is a power. This is the power source. So this is the power source connected toward the collector, not to the collector, just on the collector circuit, right? No, it's nothing. This VCC is VCC. So I could come over here and I could do this. I could come up here and I could put a resistor, and then I could come up here and put a minus 12 ohms. This would be VCC. That's the power supply that's connected in the collector circuit. If I come over here like we did before, and I come over here and put plus 5 volts, then this guy right here would be called VCC. Of course, it would. Plus 5 volts would work because that's minus 12. And then, of course, whatever I connect down here, if it's got something down here, and we put a power source down here for some reason, which later on we'll do this, then this right here would be called VDE. So I could come up here and put like a plus 12 down here, and this would be interesting. So that's the names of, that's what we call the power supply. And in analog circuits, VCC can be anything. In digital circuits, VCC is a plus 5 volt supply. So in analog, VCC could be anything. But in digital, if we see VCC, then this is going to be a plus 5 volt supply. Usually plus or minus 5%. Dang it. Okay, so what I'm going to do, so we got all the names. So VDD, this guy over here would be called what? VCC. VCC. VDD. Of course, all these, they're relative here, so we don't have a VDD here. And the voltage between the loads, between the leads, VCD. VCE. VCE is probably the most important one because this tells us if the transistor is saturated or cut off. So when we talk about less than 1 volt equal to VCC, in between them, then that's we're talking about this measurement right here. So this measurement right here tells us the region that the transistor is operating in. This measurement right here.
So this like in 1 volt is for the between.
Less than 1 volt is VCE is less than 1 volt. then it's saturated. If VCE equals to VCC, it's cut off. If it's between 1 volt and VCC, it's in what we call the active region. And we'll look at that later on. But yeah. So B, C, E, and E tells you where you. This is your common for your meter. What's on the right? What's on the right? So that tells me to get the right polarities with a meter. If I wanted to measure VCE, I would put my black lead on the emitter, and I would put my red lead on the collector. If I wanted to measure CBE, I would put my black lead on the base, and I would put my red lead on the collector. If I wanted to remember VBE, I would put my black lead on the emitter. Or, by the way, guys, we talked about this too. You don't have to put it on the collector. You got that big old metal wire right there. You can put it on. Because these leads on these transistors are going to be really, really close together, and if you slip or something like that, you're going to blow some stuff up. So if I was going to measure VCB, if I was going to measure VCB, I would put my red lead on this resistor, and then I'd put my black lead on that resistor right there. And for some reason, people think you got to get on the device itself. You don't. If you've got a resistor in series, the best thing to do is put it on that resistor lead. So all these voltages have names. So when we look them up on data sheets, they're not going to tell us the name. They're going to give us the abbreviation for it, right? So if I look at the data sheet for the, I still got it up. I do. So this says breakover voltage. Collector to emitter, and that O means the base is open. So this is definitely, this sucker is turn off, right? So that's the breakover. So that's what that means. But they don't tell us what it means. They just take for granted if you're in this thing, you know what it means. So V sub CRCEO is voltage measured collector to emitter with the base open. This would be collector to base with the emitter open. This would be base to emitter with the collector open. So every one of these are turned off. So if one lead of the transistor is open, then the transistor itself is off, right? We talked about VC sat. So if we saturate this thing, this guy right here is going to drop a maximum of 300 millivolts. So we don't say 1 volt, we said less than 1 volt, right? Should be 200 millivolts. So a transistor, if you measure 0 volts across a transistor, it is bad. Because it's got to drop something. It's not a closed switch, right? So we got some troubleshooting that we'll look at, and it'll show 2 voltage measurements. One's on the collector, one's on the emitter. There's a sign. So odds are the transistor is shorted. This is the delay time, so this is how long it would take to bring it out of saturation. So this right here, it would take about 35 nanoseconds to bring this out of saturation. No, 200 nanoseconds to bring it out of saturation. So that's how long it's stored. Yeah, because that's what happens. The delay time basically is, that's a good question too. When we switch these devices on, so if I was looking right here, and and it was setting at a high, and then I saturated the transistor, we think it's going to do this, but it's not. And we can see this on the oscilloscope. It's going to do this. It's actually going to be even when we saturate. So that's what they're telling us there. How long does it take to it's actually giving us the slope? So we can see that on the oscilloscope. Even so, I'll show y'all this even on this square wave generator here, because there's no way in the world it can go from a 0 to a 1 or a 1 to a 0 in no time at all. And we call them rise times and fall. So that's another good thing. So, okay, so get off this and let y'all see how to check a transistor with we call it an ohm meter. It's just an ohm meter that shows you the voltage that's required, right, to do that. So what we'll do is we'll use the diode scale. Oh, guys, I should have turned my camera on first. How that works.